Okay. So how do we determine this without having to graph these things? Well, if you recall, we had a couple of tests on our one variable functions that we could use, and we're going to focus in on the second derivative test. If we had a one variable, recall, just to kind of help you remember, if our first derivative was at c was equal to 0, and the second derivative was greater than 0, remember what that meant? That was concavity, so it's concave up. So what does that mean we had at c? The local min, right? And then vice versa, if f prime of c equals 0 and the second derivative was less than 0, then f of c was a local max. If the second derivative was equal to 0, remember, or doesn't exist, yeah, then this test would fall through. There's no information from this second derivative test. Okay? Well, when we go to two variable functions, it's very much analogous. Okay? There is a second derivative test for two variable functions. All right, but let me first of all mention this. When we go to two variable functions, the other complication with the second derivative is there's multiple second derivatives, right? If you've got z equals f of xy, then you've got second derivatives, what? You got the second derivative of xx. You got a second derivative by doing yy. X, y, and yx. Now, the good thing about these is, if they're continuous and so forth, those two are equal. But yeah, you've got the partial derivative with respect to x, and then with respect to x again. No, it turns out we're going to use a combination. We're going to use a combination. We're going to use d, this value, this expression, and it turns out what d is going to equal. D is going to be equal the second derivative xx times second derivative yy minus second derivative xy squared, or yx squared, either one. You could use either one, but you're going to square that. Okay? Well, it's just the combination. What it turns out, it is, just note here, D, kind of help. D is the determinant of this matrix. fxx, fxy, fyx, fyy. It's the determinant of that because, determinant fx times fyy, and then multiply these, but one is equal to the other, so you get, yeah. Okay. Yeah. And so we're going to use that to do our second derivative test for a two variable function. So here it is. Okay, so this is second derivative test for local maxes and mins for a two variable z equals f of xy function. Okay, so suppose, again, our partial derivatives are equal to 0. First partial derivatives. first order partial derivative. So the partial derivative with respect to x equals 0, partial with respect to y of f equals 0. And we're going to let, again, d equal what we just talked about. The second derivative equation there. Yeah, y, sorry. fx times fyy is xy squared. All right, so here it is. If d is greater than 0 and fxx at AB is greater than 0, then f of AB is a local min. Sort of similar there, isn't it? And you can kind of think of it this way. You know, the second derivative with respect to x, both times, that's the concavity in the x direction. Fyy is the concavity in the y direction. So anyway, if that is greater than 0, then f of AB, that's a local min. B, if d is greater than 0 and fxx AB is less than 0, then FAB is the local max. And then the third one, if d is less than 0, FAB is a saddle point. And I guess we could show this one, verify this one real quick. What was our other one? Z, f of xy was y squared minus x squared. Okay, I think this will work. All right, so we know it's 0, 0, the critical point. Yeah, so we need the fxx, so didn't write fx. Fx is negative 2x, so that'd be negative 2. Fxy, so we do the partial derivative with respect to x, and then with respect to y now, so that'd be just 0, wouldn't it? And then fyy, f with respect to y was 2y, so that'd be positive 2. And then fyx, which we don't really need, is 0, but either way, we knew it was 0. Okay. All right, so what do we got for d here? D is fxx, so we take negative 2 times fyy, which is positive 2, subtract fxy squared, so it'll be 0 squared, so that's negative 4. Hey, how about that? Got d is less than 0, don't we? And so it's a saddle point, just like we saw. Okay? Try one more real quick. Okay. All right, so let's find, because there's just a little twist or two that comes up. Squeeze this in. All right, so let's find. Oh, you could do it. You could come up with it with both. You could do it with y, yeah. So we got 3y squared minus 2y cubed minus 3x squared plus 6xy. Yes. Okay. All right, so we need the first derivatives, partial derivatives. So that would be what? Partial with respect to x. negative 6x plus 6y. And then the partial y would be 6y minus 6y squared plus 6x. Set them equal to 0. And so it's just a system, right? Yeah, it's just a system. But it's not too terribly bad, is it? Because we've got 6x in both of them, so you solve for x or 6x, whatever. Yeah, I think we are. Divide both sides by 6, yeah, sure. So y would equal x, yeah. So if we plug that in, divide this one by 6, we have y minus y squared plus x equals 0. And so, yeah, if we plug in x to be y over here, we have 2y minus y squared equals 0. So we'd either have y, positive 2, isn't it? So we have y equals 0, and then 2 minus y equals 0, so that would be y equals 2. And so there's two critical points here. Now, recognize critical points, we need an x and a y, and so what would the x be here? Well, y equals x, so x would be 0, and then x would be 0 for that too. So we're talking two critical points. All right. Whoops, I should have left that up there. Leave that up here. Okay. What was it? It's negative 6x plus 6y. Okay. All right, so we need to look at 0, 0, and 2, 2. And so we need that d value for both of those, right? D, what is d here for 0, 0? fxx, yy, xy squared. Well, we need those second derivatives, don't we? Fxx be negative 6, okay, and fxy, so this with respect to y would just be positive 6, wouldn't it? And then fyy is 6 minus 12y. Just doing this one with respect to y, partial derivative with respect to y of that one. Okay, so at 0, 0, what do we got? So that'd be negative 6 times 6 times minus 12 times 0, since I'm doing 0, 0, minus 6 squared. Negative 72, okay? So that's less than 0. Okay, all right, so d is less than 0. What does that mean? No. If d is less than 0, it's always a saddle point.
Oh, yeah. Right, those are always greater
Yeah.
than 0.
To be a local max or min, d has to be greater than 0. Okay, so d at 2, 2, we would have fxx is still negative 6, but then fyy is 6 minus 12 times 2, which would be 24, minus fxy, so it would still be 6 squared. So that's negative 6 times negative 18 minus 36, so that's going to be positive, isn't it? 108 minus 36. 2. Positive 72. Just a second. Let me finish it. So that's greater than 0. And so, yeah, we either got a local max or min. So you go back to xx. Yeah. You got d is greater than 0. fxx is less than 0,
That's
which is concave down. So it's max. Yeah. Okay.